Now in today's lecture we will go through mole balance equation application to batch reactors and continuous flow reactors, right? In the previous video lecture we have gone through the derivation of mole balance equation, right? And the equation was, if you remember, Fj0 minus Fj1 plus integral of Rj dV is equal to dnj upon dt, right? J is any chemical species J. This is flow rate, molar flow rate, right, inside the reactor. This is flow rate out of the reactor, right? And this Rj is the rate of reaction at small volume dV, right? And this was the case when the system variables, that is concentration, temperature, rate of reaction, is not constant, right? So we considered, if you remember, small volumes, right? And in those small volumes we found the rate of reaction and then integrated the equation, right? So this was rate of generation, right, denoted by G, rate of generation inside the chemical reaction, right? And this was Nj was the rate of accumulation inside the reactor, inside the system, inside the reactor, right? Rate of accumulation inside the reactor. Now in this video lecture what we will be doing is we will see what is a batch reactor and what are continuous flow reactors, right? And if you remember, using this equation what we basically do is we find the rate we find the time or the reactor volume to convert the specific amount of reactants into products, right? What we use it for? To find the time or reactor volume, right, to convert specified amount of reactants into products. Now we will see how to apply this thing to batch reactors. First we'll understand what is a batch reactor, right? BATCH, batch reactor, right? As the word reactor, we know reactor is a plant, right? It may be a tank, it may be in the form of cylinder, right? So reactor is where chemical reactions take place, right? When we say batch means when in a reactor you put the reactants in batches, right, one after other, right? So batch reactor is that reactor where you put in or where you feed the reactants in batches, right? Once the first batch is completed, right, then you clean the vessel, clean the reactor, then you put the second batch, right? So this is your reactants feeded in batches, right? And batch reactor is a small reactor. It's used for small scale operations, right? It is not suitable for large scale operations, for big industrial operations, right, where we need the continuous flow of products. So this kind of reactor can be used in lab setup, right? This can be used by scientists in the lab, right? And this reactor involve high cost, right? There is a high labor cost involved in this type of reactor because in order to process these different batches, right, you need the manual intervention. You need someone there who can process these different batches, right, and look after the reactor. So labor cost is high, and labor cost is high, right, and is not suitable for large scale operations, right? And how it looks like, you can just look at the reactor in your book, right? It would be somewhat like this, right? This is the reactor where you can put in your reactants, where inside the reactor reactants are allowed to mix, right? And you can feed in the reactors, right? Because you have to put in the reactants, feeding the reactants into the reactant is known as charging the reactor. If you see somewhere in your book that to charge the reactor, some terms like charging the reactor, it means you are filling the reactants in the reactor, right? So from here at the top you can charge the reactor with reactants, right? And reactants are allowed to react, right? Reactants can be left for some time in the reactor, right, where they are allowed to react. And in this type of reactant we have high production, right? Rate of production is high in this type of reactant because reactants can be left in the reactor for long time, right? For long time reactants can be allowed to react, right? So this is one of the advantage of batch reactor, that it has high conversions, it has high conversion rate, right? That can be obtained by leaving the reactants in the reactor. So it has high conversion rate, it has high conversions, right? By conversions we mean allowing reactant to convert into product, right? Why high conversion rates? Because these reactants can be left for long time in this reactor, right? They can be left here where they are allowed to react, right, and mix for long time to form products. So they have high conversion rates, right? So these are some of the important things, right, that you should know about the batch reactor, right? And there is one more disadvantage of this reactor, that since I said that we would be doing this in batches, right? So there can be variability of products from batch to batch, right? So this is one of the disadvantage, is variability of products from batch to batch. B2B means batch to batch, right? That means if you have two batches, say batch 1 and batch 2, right? Once the batch 1 is completed, you then go with the batch 2, and the products that are formed in batch 1 and batch 2 may vary little, right? So this is one of the disadvantage, right? One of the disadvantage is not suitable for large scale operations, variability of product, right? And labor cost is high, right? And the other is, the advantage is your high conversion rates, because the reactants can be allowed to stay in the tank for a long time. Now let's apply this equation, right, to this reactor. Since if you look at this reactor, there is no entry, right? You cannot maintain the continuous rate of flow inside the reactor and rate of flow outside the reactor, right? So there is no place wherein you can continuously, at the time of reaction, right, you can put in the reactants, and from the other end you can take the reactants out, right? So this batch reactor has neither inflow or outflow of reactants while the reaction is being carried out, right? This inflow, one important thing is, this inflow and outflow should be at the time of reaction, when the reaction is happening, when the reaction is occurring in this tank, right? This Fj and Fj0 and this in, basically this in and out means flow in and flow out at the time the reaction is occurring inside the reactor, right? So you can see that there is no inflow or outflow at the time of reaction, at the time reaction is occurring. So here these two terms Fj0 and Fj1, both are 0, and Fj1 is equals to 0, right? Now there are some system variables. If you remember, we have done this earlier. There are some system variables that we need to consider for the reactions that are occurring in this reactor. The first one is your temperature, right, and your concentration, then your rate of reaction. There is one more, catalytic power, catalytic activity, but let's take these three in this case. Now what we will consider in this batch reaction, that the reactants are mixed, right, so well that their concentration, temperature and reaction rate is same throughout the reaction mixture, right, throughout the reactants mixture, right. What we basically mean is that the reaction mixture is perfectly mixed inside the reactor, right, so that there is no variation in the rate of reaction throughout the reactor volume, right. The reactants are perfectly mixed, right. When we say perfect, the reactants are perfectly mixed in this tank, that means it's the rate of reaction or all these system variables are same everywhere at every point, right, of this reaction mixture. So rate of reaction is same, right, at every point of this reactant mixture, right. So if you look at the mole balance equation, you have a term that talks about the rate of generation, right. There you have Rj, that means Rj stands for your reaction rate, right. So now we consider that the reaction mixture is perfectly mixed and the rate of reaction is constant throughout the reactor volume, right. So these things are important to understand, and otherwise it's simple, right. Reactants or reaction mixture is perfectly mixed, and your rate of reaction is same throughout the reactor volume, right. That means here, so this is 0, this is 0. Now we will consider this Rj dV, which would be Rj, we said reaction rate is same, right, it's constant. The reaction rate is same throughout the reactor volume, that is Rj is same throughout the reactor volume, so this Rj is constant, right, it is same, that means it is same everywhere in the reactor volume, so this is constant, right. We'll use the technique of integration. If this is constant, we can take this out of the integral dV from 0 to V, right. So this is your Rj, so this is your Rjv, right. Now if you put the value of this, right, here, this is 0, this is 0, this we have simplified to Rjv is equals to dnj upon dt, right. Therefore dt would be equal to dnj upon Rjv, right, and this dt is equals to this Rj represents your rate of reaction, right, and we know that reactants will decrease as the time progresses. Since reactants are, the concentration of reactants is going down, this Rj would be negative, right. So dn upon minus Rjv, right. So this is your equation which gives you the time that is required to convert specified amount of reactants into products for your batch reactor, right. So we can take Rj, right, out of the integral. All this, just remember, right, just know the concept behind this, why we took this Rj out of the integral, right, because we considered that the reaction mixture is perfectly mixed, right, and there is no variation in the reaction rate, right. Reaction rate is constant throughout the reactor volume. So we took that Rj out, so, and integrated that dV from 0 to V, right. What we got, we put everything in the mole balance equation, Fj0 and Fj1, that is in and out, molar rate of flow inside the reactor and molar flow of rate outside the reactor is 0. Why? Because at the time of mixing, if you look at this reactor, at the time of mixing, at the time of reaction, nothing is going inside the reactor, nothing is coming out of the reactor, right. So these two quantities are 0. So what we got here is the time, right. We can, if you integrate this further, you will get time to convert the specified amount of reactants into products. And why we have negative sign? Because the concentration of reactants go down, so we have negative sign over there, right. Now we will talk about the continuous flow reactors, right. Before this, we can take one example also. If there is some certain reaction where A is getting converted into products, right, so concentration of A will decrease, concentration of B will increase. If you remember, there were some diagrams, right, like this, right, and for products it's like this, right. So you can, what you can do from here is, if the initial concentration of A is N1, right, and if the final concentration at time t, this is your time, this is your concentration, at time t1 the concentration is N2, right. So how much time will it take for the concentration of A to go from N1 to N2, right. So you can use this equation, right, and you will integrate this equation for this limit, right, from N1 to N2, right. This is how you can use this equation, right. So here this at time t, right, initially it's N1, right, then at time t1, like I said, it's t2, t1, at time t it's t1, right. Then you can integrate the above equation to find the time, the time taken to convert reactants from N1 to N2, or what we can say is the time taken for concentration of reactants to fall from N1 to N2, right. You will integrate the above expression from N2 to N1, right. N2 would be lower limit, N1 would be upper limit, because N1 is high and N2 is less, concentration of reactants is going down, right. So this equation, the equation that we have got above, is your mole balance equation on a batch reactor, right, necessary to reduce the number of moles, and it gives the time necessary to reduce the number of moles from N1 to N2, right. What you can do is you can integrate this equation. If you will integrate this equation, you get time 2. If you integrate, you know this is from mathematics, if you integrate dt, you get t is equals to integration of, this is your lower limit N2 and this is your upper limit N1, right, dn upon Rj minus V. This is the expression, right, that tells you the time required for the concentration of reactants to fall from N1 to N2, right. This is your mole balance equation. Now let's talk about the continuous batch reactors. Continuous batch means continuous flow reactors, right. There are three kind of continuous flow reactors. One is your CSTR, continuous turret tank reactor, right. The second one is your continuous turret tank reactor. Then the other one you have is tubular reactor. Tubular is because the shape of the tubular is tubular reactor, because the shape of the reactor is it's this kind of shape, tube kind of shape, tubular reactor, right? Then is your packed bed reactor, packed bed reactor, where you have, we will discuss this one by one. First let's understand what is your CSTR, right? CSTR is continuous turret flow reactor. So continuous is the stirring, right? The stirring of the reactants is continuous, so we are using the term continuous, right? Continuous stirred tank reactor, right? And the reactant mixture, right, inside this is continuous stirred, right, such that the concentration of the reactant is same in the reactor volume, right? So that is why we call it a continuous stirred reactor. And these are the three types of continuous flow reactors that we will discuss, right? And this continuous stirred tank reactor, how it looks like, it will be like this, somewhat like this. It would be like this. From here you can feed in the reactors, from here you can take the products out, right? And inside it you have reactant mixture, inside it you have reaction occurring, right? Inside the reactor you have reaction occurring, and at the time of chemical reaction taking place inside the reaction, you can have the stream of reactant flowing inside this tank and the stream of product coming out of this reactor, right? So you have now the value of Fj and Fj1, that is the molar flow rate, right? And this continuous flow reactor, this CSTR, first is it is used for large scale operations, that is it is used for large scale industrial productions, right? And the second thing about the CSTR is we consider that the reaction is taking place at steady state, right? It is normally we assume that this gets operated at steady state and is assumed to be perfectly mixed, because we said that we have continuous stirring here, so we assume it to be perfectly mixed, right? And so there is no, since it is so well mixed, right? We have continuous stirring, due to which it is well mixed, right? That there is no time dependence or position dependence of the temperature, concentration or the reaction inside the CSTR. The same thing that we have discussed earlier, right? I'll just explain you this. The flow reactor, this is a flow reactor and this is used for continuous products from a reactor. We can get the continuous flow of products from this reactor, right? And this is an ideal reactor, as we discussed, for industrial purposes. And let's just now look at the equation. And we said that there is no time dependence, there is no dependence of position. If you remember, in the first lecture we have studied that at different positions, right, we have different rate of reactions, or at different positions in the reactor we have, at this position we may have different rate of reaction, different temperature, different concentration. At this point we have different rate of reaction, different temperature, different concentration, right? Why that happens? Because the reaction mixture is not perfectly mixed. But since this is the continuous stirred tank reactor, in which stirring is so perfect, right, that the reaction mixture, right, has these variables, the variables, all these variables in CSTR reactor is same throughout the reaction mixture, right? At every point these variables are same for CSTR, right? This is what it means, right? So now we will look at the equation, and the advantage of this is this can be used for large scale operations, right? And you have continuous flow of reactants in and flow of products out, right, at the time of reaction taking place inside the reactor, right? Now if you look at the equation, let's apply it. And one thing, the perfect mixing that I've talked about, that this is so well stirred that the mixing is perfect, right? This is not true for all. This is I mean, these kind of reactors that I've just spoke about, that there is perfect mixing, these are ideal reactors, and in reality there is no ideal reactor, right? There are some variations, right? If in terms of these variables, there are some maybe small variations, but there are small variations, right? So even CSTR is not an ideal reactor. You have some variations, right? Now let's look at the equation for all these variables. Let's look at that, right? When we'll apply this mole balance equation to CSTR, in CSTR, since conditions do not change with time, right, we said that this, because there is continuous flow of reactants inside, right, and it continuous flow of products out, so the conditions are not changing with time, and inside the stirring is so perfect that the reaction mixture has same composition throughout, same temperature, same concentration, and same rate of reaction, right? So here this dN upon dt would be 0, right? dN upon dt would be 0 because conditions are not changing with time, so this is 0, right? And if you talk about this reaction rate of generation, now we have to find this rate of generation. The rate of generation would be, now again this R is this Rj, this would be constant like we did here, right? This would be constant. We will take this out of the integral, right? Then we will integrate this dv. What we get is Rjv, right? If you put all these values here, you will get fj0 minus fj1 equal to, this is plus Rjv equal to 0, right? From here you can find the volume of the reactor that is required, right? This would be, you can find the value of, you can just this simple mathematics, right, wherein this volume would be, from here you can find the volume would be equal to, volume is equal to fj0, this, and I'll take this here, this would be fj0 minus fj1 divided by this Rj minus, right? This is your expression for the reactor volume that would be required for the flow of, that would be required to convert that specified amount of products, or the reactants that are coming from here and the products that are going out, right? So Fj and Fj0 and Fj, this is the molar flow rate, right? Molar flow rate. So Fj is your molar flow rate is obtained. This is the product of concentration of species J and the volume flow rate, right? This Fj is your concentration divided by volume. This is concentration is moles per volume. This is your volume, right? Volume per unit time. This is your volume flow rate, volume per unit time. right?